Welcome to Formula 1 Maths. This is 5.1 of the A-level Applied Maths course. We are going to learn how to resolve forces today. So let's get started. When a force is applied to an object, the force can either be parallel to the direction of motion, or the force can be inclined at an angle theta to the direction of motion. When a force is inclined at an angle to the direction of motion, it can sometimes be difficult to work with it. So the way around it is to resolve the force into two components. One of them will be parallel to the direction of motion, and the other will be perpendicular to the direction of motion. What you need to also realize here is this: a force cannot be on the same diagram as its component. So the force that was here in bold has now been replaced by the horizontal component here and the vertical component. Before we go and learn how to resolve forces, let's do some recap of some basic trigonometry. This is a right angle triangle with the angle over here. This means that we've got an adjacent side A, which is next to the angle, an opposite side which is facing the angle, and a hypotenuse side which is the longest side. Using SOHCAHTOA, we know that cos theta is equal to adjacent over hypotenuse, which implies that adjacent is equal to h cos theta. Similarly, sin theta, which is opposite over hypotenuse, implies that opposite is equal to h sin theta. We are going to use this knowledge to resolve forces into two components. So let's go and do that. We've got this force here that we need to resolve. The force is inclined at an angle theta to the horizontal. So this force can be resolved into a horizontal component, which is F cos theta. Note that this is similar to this one here. So in this case, our F was h over here. In the same way, the vertical component is F sin theta, which is also similar to this one here. So here, the h over there is replaced by F. So this is basically how to resolve forces. Now, as you know, a force is a vector quantity. So it can also be expressed in terms of vectors. So since this is a horizontal component that is in the I direction, and this is a vertical component that is the J direction, we can express F in vector form as F cos theta I plus F sin theta J, or simply F is equal to all that. So let's go and use this knowledge to solve some questions. We've got two questions here, A and B. It says that each of the following diagrams shows a box on a smooth surface acted on by a single force. In each case, work out I, the acceleration of the box, I, the normal reaction between the box and the floor. So first of all, we draw a force diagram with the resolved forces. So originally, the forces acting on the box are this 60 Newton force, the weight of the box, which is 20 G, and a reaction force R. But we need to resolve the force, 60 Newton force, to get 60 cos 30 over here, 60 sin 30. There are only 4 forces acting on the box right now. These are the weight, 20 G, the reaction force due to the surface, and there is resolved forces, this one and that one over here. Please note that the only force producing a motion is the 60 cos 30 newtons, because the question says that the box is on a smooth surface. This means that there is no friction. So the only force that will produce a motion is the 60 cos 30 Newton force. So for the acceleration, we have to consider the horizontal direction and use Newton's second law of motion. So our force F is 60 cos 30. Our M is 20 kilograms, and A is the value we are looking for. So we rearrange to get this, simplify to get 3 cos 30, and finally evaluate to get 2.6 meters per second squared. For the normal reaction between the box and the floor, we need to consider the vertical direction. Now, there is no motion in the vertical direction. The box is not moving up or down. So we can say that the total upward forces must be equal to the total downward forces. So looking at the forces right now, we've got 2 forces acting downwards, 20 G, which is the weight, and a 60 sin 30 Newton component of the 60 Newton force. The only force acting upward is the normal reaction R. So we can form this equation here. R is equal to 60 sin 30 plus 20 G. Evaluate that, and we are going to get 230 newtons. So that's A. For B, we do the same thing. Draw the force diagram. We've got 10 G acting downwards. Normal reaction R1 is acting upward. Then we resolve the 20 Newton force into its 2 components. Again, because there's no friction acting, the only force that is producing a motion is a 20 cos 60 Newton force. So using Newton's second law of motion, we have 20 cos 60 is equal to 10 A1. Rearrange to get this. Simplify to get 2 cos 60. And evaluate to get 1 meter per second squared. For the normal reaction, we consider the vertical direction. Again, there's no motion vertically. The box is not moving up or down. So we can form our equation by equating the upward forces to the downward forces. So in this case, we've got two forces acting upward, R1 and then the 20 sine 60 Newton component of the 20 Newton force. The only force acting downward is the weight, which is 10G. So this time our equation will be this. Rearrange to get that, and then evaluate to get 81 newtons. So that was question 1. Question 2. It says each of the following diagrams shows a particle being acted upon by two forces. In each case, work out the magnitude and direction of the resultant force acting on the particle. These are the type of questions where you can use two methods to solve them. We can use either resolution of forces or another method called the triangle of forces. I'm going to do a follow-up video on triangle of forces. But for now, let's learn how to solve this using resolution of forces. So first thing we do here is to resolve the forces like this. That is for the 50 Newton force, and then this one for the 20 Newton force. We are looking for the resultant force. To get the resultant force, we need two components. We need the horizontal component of the resultant force and the vertical component of the resultant force. To get the horizontal component of the resultant force, we need to add the horizontal components of the resolved forces. And knowing that forces are vector quantities, you need to take into consideration the direction of the forces. So for the resultant force, we'll calculate the horizontal component first. And taking this direction here to be positive means that this vector going this way is negative. So for the horizontal component of the resultant force, we add these two forces to get this. So Rx, which is the horizontal component of the resultant force, is 20 cos 30 minus 15 cos 30, because this direction here is negative. If you evaluate that, you get 6.71. We do the same thing for the vertical forces. That will be 20 sine 30 acting up plus 15 sine 45 because it's acting upward. And so we add them together to get that. So let's try to sketch this situation here for the resultant force. So we've got a situation like this. We've got the horizontal component, which is 6.71. The vertical component, which is 20.61. And to get the resultant, we need to add the two vectors. And this means a vector that will run from the tail of the first vector to the head of the second vector. And that will be this. So that is the resultant force. And so we can use Pythagoras' theorem because this angle here is 90 degrees. So let's go and do that. We get, by the way, this is the symbol for the magnitude of the resultant R. So do your substitution. You get that. Evaluate to get 21.7 Newton. So this is the magnitude of the resultant force. For the direction, we calculate this angle here. So we're going to use trigonometry to get tan theta equals to 20.61 over 6.71. That implies that theta is equal to tan inverse of all that. And this evaluates to 72. We then go and formally state the direction as 72 degrees above the direction of the vector I, because this direction here is in the I direction. So for B, we do the same thing. Resolve the forces to get that for the 10 Newton force and that for the 12 Newton force. We add the horizontal forces. They are both in the positive direction, so we get that. And for the vertical forces, one is in the positive direction, which is acting upwards, this one. The other one is in the negative direction. So adding that will give you this minus 2.71. So it means that we've got a situation like this. Sketching it, we've got a situation like this. And we know that this is 17.9 and that is 2.71, which will give us a resultant force like that. Now, given that this is 90 degrees, we can use Pythagoras' theorem, subdue the substitution, and we get 18.1. So 18.1 is the magnitude of the resultant force for B. Therefore, the angle, we go and calculate this angle here. Let's call it theta again. And then we have theta is equal to this. Evaluate to get 8.6. Note that in this case, this is below the direction of the I vector. So we formally go and state our direction as 8.6 below the direction of the vector I. And that's it for this video. Like I said, I'm going to do a follow-up video and use triangular forces to solve the same two questions here so that you know how to use that method as well. Thank you for watching, and I'll see you in the next video.